Everybody. Thanks for the introduction. So before I jump into my talk, I'll just tell a little bit about what we do at S&P Global and why I'm talking about deep learning and natural language processing. So at S&P Global, I work for a division called Market Intelligence, and our primary product is data, financial data, energy sector data, and most of it comes from openly available sources. So anytime a company releases their earnings or anything like that, they will publish a file somewhere out on a website, and our company will go out and scrape that. And then our traditional business model has been having folks read those documents, read through them, type in useful information, and then we productize that and make it into, and we sell it to our customers. So then they can do financial research, make the important decisions that make them all sorts of money. So the nice part about having that as our primary business model is that we've been doing this for 20 or 30 years, so we have tons of really, really nicely curated gold standard data sets. One of the problems with that business model, though, is it's not really efficient to have thousands of people reading through documents and typing in information, no matter how streamlined you can make that process. So our team started a couple years ago with just a couple of people internally at S&P realizing that we can probably optimize some of these processes, and a lot of that optimization is going to be applying natural language processing techniques to these raw documents and trying to just optimize our pipelines and also try to enhance some of the pipelines so we can pull out new data and automate a lot of those processes that we don't want to have to do. So that's why we do a lot of natural language processing, and kind of the state of the art for natural language processing these days are neural methods. So lots of people talk about deep learning. There's lots of cool stuff that you can do with deep learning. It's not always the answer, but in a lot of cases, and particularly a lot of cases that we're tackling, it is a really good solution. So first I'm just going to talk quickly about neural methods for natural language processing and how they differ from traditional methods. Then I'm going to talk about the shapes of natural language processing tasks. And this is one thing that I'm going to try to come back to throughout the talk, and that is how do we look at the shape of a natural language processing task, break that down into component chunks, and then apply the right architecture from a neural net for that particular task. After that, I'll jump right into Perceptron text classification. So a Perceptron is just like a kind of easy introduction into deep learning. So who knows what a Perceptron is? Bunch of people? All right. So I'm just going to walk through the basics of what that is to kind of get everybody up to speed. And then I'll talk about local versus global text representation. So how we actually represent text has kind of changed over the past few years because largely in part due to deep learning algorithms. And then I'll finish off with going beyond just global text representations and developing contextual representations using sequence models. And this has actually been really, really popular in the past, I don't know, year or so with the advent of some new models like Elmo and BERT. They're naming them after Sesame Street characters for some reason, but that's cool with me. So let's jump right in and talk about why we want to use neural methods for natural language processing. So in the past maybe 5 years or so, we've really moved to using neural methods for most of our natural language processing tasks. If you go to any computational linguistics department, maybe 5 years ago they might have been using lots of hidden Markov models and other sorts of sequential models like that. And if you look at the cutting edge research that's published on Archive these days, most of the computational linguistics departments are using neural methods just because they work so well. It's kind of similar to the ImageNet revolution with CNNs in, I don't know, like 2013 or whenever it was, where there were lots of other different image processing techniques being used for image classification, and then CNNs were introduced and they kind of just took everything by storm. So traditional NLP methods, I'm not here to trash them. They work really, really well, and they've been working well for a long time. But they do have a couple of drawbacks. One of them is that they have model rigidity. So you can only handle certain tasks. You can handle them really well, but they're not flexible to handle nearly every task. And natural language modeling is really, really complex. There's so many different ways to represent language and to process language, and that's ever evolving. So they're kind of rigid, and they're built on local word representations. So most most traditional tasks use these local word representations, and we're losing out on some really, really rich context that we could be leveraging when we use those types of representations. And I'll get into what I mean by that in a few minutes. So what we gain by using neural methods is one, it's a really, really active area of research, and it's been shown to set new benchmarks year after year, and I mean, even in some cases, month after month. And we can learn these global and contextualized word representations, which is really, really powerful in the area of in areas of things like transfer learning, where you take what other people have already done and apply it to your problem, and just automatically gain some lift on whatever modeling task you're doing. And the thing that I'm going to focus on mostly for this talk is purpose-built architectures. And this is my favorite thing about deep learning in general, and specifically for NLP. I was a huge fan of Legos when I was a kid, and I kind of see this and the ability to kind of piece together different parts of neural net architectures as just like a higher level form of Legos. So you kind of figure out what your task looks like, and then you're like, well, I know that this piece can do this part of my task, and this piece can do this part. So you just kind of piece them together, and you can come up with some really, really intricate solutions for complex problems by just piecing together these really simple structures. So let's jump into what the general shape of natural language processing tasks looks like. So I would argue if there's folks in the audience that do natural language processing, don't ding me too much on this slide. This is a generalization, but a lot of natural language processing tasks can be broken down into, you have some document or some chunk of text. You run that through some vectorization process that produces a vector, and then you run that through some sort of a task, some machine learning model or something, and that produces some other sort of a vector. Maybe for binary classification, this would just be a single number, which would probably represent the probability of whether or not that document is, or that chunk of text is a particular thing. So maybe this is relevant for this particular workflow, or this isn't relevant for this particular workflow. If we wanted to do multi-class classification, then we might output a vector of probabilities, maybe normed so the sum of all of them equals 1. But again, notice that nothing to the left of that last little bit has changed at all here, just from this high-level standpoint. For sequential modeling, or sequential classification, for problems like language modeling or part of speech tagging or named entity recognition, you might take just like a single small span of text, tokenize that, and create a vector for each element in that short span of text, and then run each one of those elements through your task, producing another output sequence of potentially probabilities or something like that. Now, the reason that I like deep learning so much is because with traditional machine learning workflows, we spend 80 to 90% of our time here, and I would argue upwards of like 98% of your time, depending if you look on the entirety of a project lifecycle. And this is really the stuff that I'm the most qualified to do. I understand machine learning algorithms. I understand the ins and outs of how I actually model things. So I want to be spending most of my time here. But normally, I'm only spending 10 to 20% of my time here with traditional machine learning workflows. So what deep learning allows us to do is, just in general, and this is not just specific to natural language processing, but it allows us to handle this vectorization as a part of our modeling pipeline itself. So instead of trying to feature engineer really useful features from text or images that I think are really representative of the tasks that I'm trying to solve, I can just have my machine learning model learn the things, learn how to represent my data in a useful way for my problem. And I mean, if you do it right, you can have it learn representations that may not necessarily be intuitive to you, but that can give you lift on top of just doing it on your own. So that's really, really, really interesting to me. So we'll jump quickly into Perceptron text classification, and we'll go through this fairly quickly. And this is just to give you, for those of you that haven't done any deep learning or have never worked with neural nets, this will just give you a little bit of a flavor for what you actually do when you build a neural net. So for the time being, let's just focus on this task part. So we have some input vector. We're going to send it through some task to produce some probability. And the simplest, for the vectorization, we'll just assume that we've done some count-based vectorization technique like term frequency inverse document frequency vectorization. I'll get into a little bit about count-based representations in the next slide, so just bear with me for a minute. So we'll assume that we've already converted our text into a vector here. We're not doing that, that deep learning vectorization. And how can we actually carry out this task? The simplest model that we could have is called a perceptron. So over here on the right, that's our input vector, or on your left, I guess. That's the input vector. And then we have this hidden layer right here. And I'm just assuming a linear layer. And I'll get into what that actually looks like in just a second. And then because I want to do classification, I take the output from this hidden layer, which is just going to be a single number or a vector of dimension 1 with length 1. And I'm just going to squash that down. I'm going to use a sigmoid function to just take that unbounded floating point number and just squash it down to in between 0 and 1 so I can produce a what I want to interpret as a probability. Now, if I wanted to turn this into a regression problem, I can just get rid of that softmax. And then this thing is a regression problem. So if I wanted to do perceptron regression or something along those lines, I could just get rid of that. So that's kind of dipping your toe into the power of these deep learning models and the architectures that you're developing. They can change by just swapping out the individual pieces. I can go from classification to regression by just taking out one little piece. So what does this actually look like under the hood? So what's inside this task box? It's really just a vector of weights that I'm optimizing. And I take the dot product of my inputs with that vector of weights, and taking the dot product of two vectors produces a scalar. So then I have some scalar number. I squash that down with my sigmoid function, and then I have my output probability. And I do this a whole bunch of times, every time finding the difference between my output probability and my expected probability for or my expected class for a supervised learning problem. And then I update these weights every time with how much each one of those weights contributed to my wrongness for that particular example. So I just run this a whole bunch of times, optimize my weights, and then boom, I have a text classifier. So if I wanted to make this a multi-class classification problem, all I really need to do is extend that hidden layer to just be 3 units instead of just 1. I apply my sigmoid to each one of those, or maybe a softmax if they're not mutually not mutually exclusive. And then I have 3 output probabilities. So how does that look in my task? Well, now I just, instead of having a vector of weights, I just have a matrix of weights. And all of the deep learning packages that anybody would use, TensorFlow, all of those things, have structures that just handle all of this for you. They handle all of that optimization, the back propagation to figure out how much each one of those weights contribute to your overall wrongness or to your loss. And this is just really powerful. And the thing that I like the most about it is to go from that single vector to this matrix right here. I just change a single number in my so I like to work in PyTorch. So in PyTorch, I would just create a linear layer with my input dimension as one side of it, as one input parameter, and then my output dimension would just change from 1 to 3. Boom, I've gone from a binary classification to a multi-class classification by changing that. You might have to change something else like your loss function, but those things are trivial. So now I'll talk a little bit about local versus global text representations. So let's look back at the problem of creating a vector representation for our text. I said before that I was just going to use a TF-IDF count-based approach for vectorizing my text here. But how can we actually come to a vector representation of our text? Well, now let's just focus on how we can come up with a vector representation for a single word, and then we can get to how we would come up with a vector representation for a longer span of text. So if I want to create a vector representation for just a single word, the simplest thing that I can do is just count all the individual words that I have in my corpus and just create a sparse vector out of all of my words. So I have apple here. Apple is the first word in my vocabulary. I just create a 1 and then all zeros. And the length of that vector is going to be the number of words that I have in my corpus. So you can see that that may become problematic pretty quickly because you might just have 3 words in your corpus. These things are all orthogonal to each other in this representation. You can think of them as basis vectors in some high-dimensional space. And as I add more and more basis vectors, I'm creating this really, really high-dimensional space. So what that means is that this matrix here that represents all of my entire corpus gets really, really, really wide really quickly. So you're automatically, when you're working with text data in these traditional local vector representations, working with really, really high-dimensional data. And when I say count-based approach, I'm really saying if I want to represent a document, I'm just going to add up all my ones and zeros for these long, really, really wide vectors for every word in my document. Count those up. Maybe I'll normalize it by how many documents they occur in, but I still have these really, really wide vectors. And you can think maybe I'll just cut off the words that don't occur that frequently, but for different tasks, those words might be really, really important in your classification or in whatever your sentiment analysis, anything that you're working on. So that doesn't always seem like the best approach. So what if we, instead of doing this, what if we figured out some way to just represent them as a dense matrix representation? So with this sparse matrix representation, we're not only creating this really, really wide matrix, we're also not gaining any, or not capturing any information about the relationships between those things. So what if we could do that? What if we could come up with some sort of dense vectors where maybe the distance between baby and child in this lower dimensional space now is shorter than the difference between baby and Texas. So capturing some semantic relationships between the actual words that we're modeling. Well, that would be really, really useful. And fortunately, I think it was in the sometime before 2010 or shortly after 2010, we came up with a highly optimized approach for doing this in an unsupervised manner, meaning that you could just take tons of documents, throw them at this algorithm, and it would learn by what words are next to what other words, some relationships between those things, and it would just give you these vectors out. So the first algorithm that was really popular for that was called word2vec. It's still used a lot. There's another one called glove that's more of a statistical approach, but nonetheless it gives you these dense vectors. And now there's newer approaches, like I said, like Elmo and Bert, that capture even more information about your words in these vectors. So by just going out, grabbing some of these word vectors from the Glove website or different websites, you can just download them, feed these into your model instead of that one-hot encoding representation, and usually get a decent amount of lift. You have to be careful. You don't want to just average these things because that'll wash out some of your information. But if you do it right, you can usually gain some lift on your model from just doing that. So that works in a lot of different cases, but just consider this sentence for a second. I'm going to book our vacation, then relax and read a good book. So can anybody see an issue with this sentence and using the global representations that we had? Anybody? Shout it out. Book, right? So what do I want to use for this word here? Do I use the same vector that I got from my unsupervised approach? What if my unsupervised learning approach, what if my word vectors were trained on all of the words from Barnes & Noble's website or from some sort of text website? Well, then this particular usage of the word book would probably be really, really underrepresented in there. So it wouldn't be a good representation for this particular usage. Now, if I trained my unsupervised vectorization model on something like Expedia's comments or something, then this might not necessarily be a great representation. So just consider another sentence for a second. What about, I don't really hate horror movies, but I hate comedies. Now, I don't know who would hate comedies, but nevertheless, what if I was using text like this to do some sort of like sentiment analysis for movie recommendations on a website? Well, how do I make sure that I include the word don't in really hate horror and not in hate comedies? My point here is that context matters. With these things, you can't just take your global text representation and just run with it, because in a lot of particular use cases, the context around those words can greatly modify the meaning of those words. So it's really useful in a lot of tasks like this where you're modeling sequences of things. So if I'm trying to figure out the part of speech of a particular word, well, I want to know what came before and after it. So the word vector for that word should tell me, like, if this is an animal or something like that. You oftentimes see all of your animals clustered together, or all of your names clustered together. So that'll give you some information. But a lot of times, if you see a whole sequence of words, there's some meaning in that sequential relationship. So for a lot of tasks like this, you might start out with a single sentence, vectorize it into a whole bunch of words, and we want these words to capture not only the semantic relationships between the words for a super large corpus, but also the contextualized semantic relationships between the words as they appear in the sentence. And then we can feed them through our task and come up with some output probabilities for whether or not this is an animal, or whether or not this is a noun or a verb or something. So with deep learning, we usually use sequential models to handle this. So a sequential model at its barest form just takes in a single vector into some sort of a unit in the model, and then it passes that information both out as an output vector and also to the right. So this is a recurrent neural network that we're looking at here. And we feed the information, oh no, I think I just pressed stop. There we go. We feed the information both up and right. And what this does is our output vector for the word the here would only have context from everything that it's seen before, which is nothing, so it wouldn't be a contextualized version per se. But as we move further and further down, the output for the word fox would have some information baked into it from all the previous words that it's seen. So this would be, the output vector here would be a contextualized version of everything that's come before it. So this gets really, really powerful, because now we can feed this vector into some sort of a model, and this vector is cognizant of the fact that it's had all these other types of vectors preceding it. So this gets really, really powerful really quickly. So this is useful in things like language modeling, where the task is to predict the next word in a sequence. This is like a probably much lower level way, but a way that you could do something like Google's autocomplete. When you type a query into the Google search bar and it completes with a whole bunch of different queries dropped down, you can just look at probabilities for sequences of words occurring, and this is a model that would do something like that. So models like this are actually the fundamental framework that's replacing a lot of the computational linguistics algorithms. So whereas before you might have used like a hidden Markov model or something like that, a lot of them are using this as at least a component of their neural models. Another thing that you could do is named entity recognition. So you might want to be able to predict whether or not a particular token is an animal or a person or an organization. And these, I don't have any examples of it here. I only have fox and dog as animals. But these tokens can span multiple, or these labels can span multiple words as well. So what if I had Anaconda Incorporated, for example? If I was looking to tag that as an organization, it may or may not, I mean, depending on your task, be important to have the incorporated on there. So you could look for spans where you have two tokens that are a single thing, like an organization. And this is also used for things like part of speech tagging as well. But it also gets really, really interesting if you think of, well, if this is a contextualized vector representation of the word fox and everything that came before it, Well, this vector down here has information encoded about the entire sentence in there. So this last vector, the last output from your recurrent neural network, will be a contextualized representation of your entire sentence. So a lot of times these models can be used for things like sentiment analysis, where you can take into account the fact that I have like not before the word hate, and really realize that I'm not saying that I hate something, but I'm saying that I do not hate something. And depending on what type of classification approach you would be using traditionally, if you used a count-based approach, you might see that the word hate appears in this, and your model has learned that every time there's hate in this sentence, that's automatically a negative sentiment. But by looking at a sequential model that can take into account the contextualized representation of your text, you could see pretty easily that your model could figure out that that is not necessarily a negative sentiment. So I've been saying that we can do all of these different types of tasks using these recurrent neural networks, but a vector doesn't necessarily, this doesn't just output the vector of probabilities for your classification. So what we do is we just take something like our simple perceptron, or maybe just a linear layer that you're learning, because that's really all that the perceptron is, and just slapping that on top of those output vectors. So maybe we have a binary classification, and we just want to know, is this output vector coming from the input token, is this an animal or not? So then we would just have a binary classification problem. So you just take that contextualized vector from your output from your recurrent neural network, and just feed it into a perceptron, and that just tells you whether or not that input token was an animal. Now, you can do this for every single vector in your sequence, in which case you're doing sequential classification of every word, or you could just slap a perceptron on the very last one and figure out something like sentiment. Now, that's really, really powerful for things like this, and this is just kind of scratching the surface of the type of stuff that you could do with this. So you could think of doing something simple like this, where you're just putting a single perceptron at the end. But let's say that we had some more complex task where we had some really, really long document, and then we wanted to look at that document and figure out, well, what are the portions in this document that are the most critical for my company to be reading? Let's say you have people at your company that need to read through 1,000-page documents, and you want to just be able to highlight and quickly link them to the really, really important sections that are maybe this is like legalese and it's a lawsuit, and you want to figure out quickly if this is a lawsuit that I need to be worried about, or this is just a frivolous lawsuit. Now, don't get me wrong, I'm not saying that S&P gets sued a lot or anything, so this is not the stuff that I do, but just as an example. So how could we actually break this problem down using the building blocks that we saw, that we've seen so far? So we could start by just taking each sentence, running them through something like the recurrent neural network that we saw to produce a vectorized version of each one of the tokens in there. And then we could just grab that last vector, and then that's a vectorized, contextualized vector representing each one of the sentences in there. And then let's say that each one of those sentences, we usually see like big sections of the legalese that is important to determining whether or not a lawsuit is frivolous. We see big chunks of those. So we would expect that there would be some sequential nature to nothing we care about, and then a big chunk of stuff we care about, and then maybe nothing that we care about, and then another chunk of things that we care about. So you could think of taking each one of those sentence level vectors, passing them into another recurrent neural network that's creating a new contextualized representation of that single vector for the sentence that's aware of the sentences that came before it. So now this is a single sentence, and then the one above knows about the sentences that came before. So if I had a sentence that I cared about in this document, chances are the next sentence is probably going to be one that I care about as well. And then we could just run each one of those into our perceptron classifier at the end to just say, do we care about this or do we not care about this? And then that would just highlight the individual sentences in the document that we would actually care about. So these pieces that I have here, although this looks really complex, it wouldn't be that hard. This would probably be maybe 10, 12 lines of PyTorch code. So this looks fairly complex, but it wouldn't be that difficult to implement because these libraries make it easy to just build this entire thing in one line, or build that whole perceptron in one line. So this stuff gets really, really powerful really quickly. And it's really fun and interesting, and that's what keeps me doing what I do, to just think of, well, I have this arbitrary task where I need to solve this problem, and this is what I have for input text. And how do I get from here to here? And just drawing out diagrams like this and figuring out how you fit all those pieces together is really what keeps me going. So with that, I'll finish up, and thank you for your attention.